Scientists recently confirmed that the dwarf planet at the edge of our solar system has a climate system unlike any other world ever studied. The James Webb Space Telescope, looking at Pluto in wavelengths no instrument had been able to use before, measured the thermal glow of its atmosphere and found that the air itself is being cooled by a suspended layer of organic particles. No other planet, moon, or known body in the solar system regulates its temperature this way. That single fact rewrites a story most people thought was finished. For nearly a century, Pluto has been treated as a kind of cosmic afterthought, a small, frozen, harmless world at the back of the textbook, the little planet that got demoted, the lovable outcast. The new measurements describe something very different. They describe a world where the surface is made of frozen gases, where the sky is a thin column of organic poison, where matter physically leaks from the atmosphere onto a neighboring moon, and where the atmosphere we currently observe may be in the early stages of freezing solid and falling out of existence. To understand why this matters, it helps to start with how little we actually knew about Pluto until very recently. The world was discovered in 1930 by a young astronomer named Clyde Tombaugh, who spent months comparing photographic plates of the night sky in search of a faint point of light that shifted against the background stars. When he found it, the public reaction was enormous. A new planet, the ninth, a member of the solar family. For decades after that discovery, Pluto remained almost entirely a mystery. It was too far away and too small for even the best telescopes on Earth to resolve as anything more than a dot. Astronomers could measure its orbit, a strange elongated path that takes 248 Earth years to complete. They could estimate its size, which turned out to be surprisingly small, only about 2,380 kilometers across, roughly two-thirds the diameter of Earth's moon. In 1978, astronomers discovered that Pluto was not alone. It had a large companion, a moon named Charon, roughly half its diameter, orbiting so close that the two worlds form a tidally locked pair. Over the following decades, 4 more tiny moons were identified, and faint signs of an atmosphere were detected as Pluto occasionally passed in front of distant stars and bent their light. But everything remained vague, glimpsed from billions of kilometers away through what amounted to a frosted window. The Hubble Space Telescope helped a little. It could resolve Pluto as a small disk with blotchy bright and dark regions, enough to suggest that the surface was varied, but not enough to explain what was happening on the ground. The real transformation came in July of 2015, when NASA's New Horizons spacecraft completed a 9.5-year, nearly 5 billion kilometer journey and flew past Pluto at almost 50,000 kilometers per hour. The flyby lasted only a few hours, but the data sent back over the following months changed everything. The photographs were extraordinary. Pluto was not a featureless ice ball. It had a vast heart-shaped plain of nitrogen ice, informally named Tombaugh Regio after its discoverer. Inside that heart sat Sputnik Planitia, an enormous basin about 1,000 kilometers across, filled with nitrogen ice so geologically fresh that it carried almost no impact craters. The ice was organized into polygonal convection cells, each tens of kilometers wide, where warmer nitrogen rises from below, spreads outward, cools, and sinks again on a slow churning cycle that resurfaces the basin roughly every 500,000 years. Surrounding this active plain rose mountains of water ice, some reaching 3.5 kilometers high. At temperatures near -230 degrees Celsius, water ice on Pluto stops behaving like ice in any familiar sense. It becomes structural bedrock. It does not flow. It does not sublimate. It forms a rigid crust on which the more volatile ices migrate and change. Other regions of Pluto were stained dark and reddish-brown by tholins, complex organic compounds produced when ultraviolet sunlight breaks apart methane and nitrogen high in the atmosphere, sending a slow chemical rain down onto the surface. And then there was the haze. As New Horizons looked back at Pluto after closest approach, it captured an image of the world backlit by the distant sun. The thin atmosphere glowed in concentric layers of blue, extending more than 300 kilometers above the surface. The blue color came from sunlight scattering off tiny suspended particles of organic material. It was beautiful, almost delicate, and it reinforced the affectionate image of Pluto as a small, strange, but charming world. The problem is that the New Horizons flyby, for all of its visual power, was a snapshot. The spacecraft swept past the system in a matter of hours. Its cameras worked in visible and near-infrared light. It could not measure thermal emission across the wider mid-infrared range where cold objects radiate most of their energy. It could not separate the heat coming from Pluto from the heat coming from Charon, because at the distance from Earth, their infrared signals blended together into a single, unresolved point. It could not return again and watch how the world changed over time. It told us what Pluto looked like at one instant. It could not tell us how Pluto actually works. That is the gap the James Webb Space Telescope was finally able to close. Webb was not designed specifically for Pluto. Its primary missions involve distant galaxies, star-forming regions, and the atmospheres of planets orbiting other stars. But its capabilities make it the most powerful instrument ever pointed at the outer solar system. Its primary mirror, 6.5 meters across, collects far more light than any previous space telescope. Its instruments operate across the infrared, from wavelengths just beyond what human eyes can see all the way into the mid-infrared, where extremely cold objects emit their peak thermal radiation. The instrument that mattered most for Pluto is called the Mid-Infrared Instrument, often abbreviated as MIRI. It works in wavelengths roughly from 5 to 28 micrometers. This is the spectral range where cold objects glow. Everything in the universe with a temperature above absolute zero emits thermal radiation, and for an object as cold as Pluto, that radiation peaks deep in the mid-infrared. MIRI can detect this faint glow, measure how its intensity changes with wavelength, and extract information about surface temperature, surface composition, and atmospheric behavior that no visible light camera can access. MIRI also had one specific advantage that no previous instrument possessed. Pluto and Charon orbit each other at a separation of only about 19,600 kilometers. From Earth's perspective, almost 5 billion kilometers away, that gap appears tiny. Earlier infrared instruments could not tell them apart. Their heat signals blurred into a single point. Webb's combination of mirror size and precise infrared optics finally provided enough resolution to separate the two worlds in the mid-infrared for the first time, using careful photometric techniques and the known geometry of the system. The observations happened in two stages. In 2022, MIRI measured the thermal emission from the Pluto-Charon system at 18, 21, and 25 micrometers, tracking how the heat output changed as both worlds rotated. In 2023, MIRI obtained a full mid-infrared spectrum of Pluto, from roughly 4.9 to 27 micrometers. This was the first time anyone had ever measured Pluto's thermal emission across this entire range. The data was transmitted across billions of kilometers, processed by international research teams, and finally published in the journals Astronomy and Astrophysics and Nature Astronomy in 2025. To understand why these measurements matter so much, you have to understand what mid-infrared light reveals that visible photographs cannot. A photograph shows reflected sunlight. It tells you what a surface looks like. Bright regions reflect more light, dark regions absorb more, and color hints at composition. But a photograph cannot tell you how warm something is, how energy flows through an atmosphere, or what processes drive a planetary climate. Mid-infrared observations are different. They do not show reflected light. They show emitted heat. Every surface and every gas above absolute zero radiates thermal energy, and that radiation carries a spectral fingerprint that reveals temperature, composition, and the way materials interact with incoming sunlight. If suspended haze particles absorb solar radiation and re-radiate it as heat, that process is invisible in a photograph, but unmistakable in a thermal spectrum. This is why Webb's scan of Pluto qualifies as the first true look at the world in a scientifically meaningful sense. We had seen Pluto before. We had photographed it in stunning detail. but we had never measured its thermal behavior in the wavelengths where the most important atmospheric processes show themselves. Webb did not give us a prettier picture. It gave us a fundamentally different kind of information. And the first thing that information revealed was something deeply strange about Pluto's atmosphere. Before Webb, scientists already knew Pluto's atmosphere was thin and exotic. New Horizons had confirmed it consists almost entirely of nitrogen gas, with small amounts of methane and carbon monoxide. The surface pressure is about 1 pascal, roughly 100,000th of Earth's atmospheric pressure at sea level. Standing on Pluto, you would be in what any engineer would call a hard vacuum. Yet that wisp of gas is enough to drive weather of a kind, to push ices from one region to another, and to support a towering column of haze stretching hundreds of kilometers above the surface. In 2017, a research team led by planetary scientist Zhang proposed something radical. They suggested that Pluto's haze was not just a chemical byproduct, but the main driver of its climate. Their models showed that haze particles absorb ultraviolet sunlight during the day, warm slightly, and then radiate that energy away as infrared light. This radiative cooling, they argued, would be far more efficient than the cooling that gases alone could produce. If they were right, it would explain a puzzle from the New Horizons data. Pluto's upper atmosphere was roughly 30 degrees Celsius colder than the gas-only models predicted. The haze, in effect, was acting like an enormous distributed refrigerator, absorbing solar energy and dumping it back into space as infrared heat. It was an elegant hypothesis. It was also untestable at the time. To confirm it, you needed to measure Pluto's mid-infrared emission with enough precision to detect the thermal signature of the haze itself. No existing instrument could do that. The signal was simply too faint, buried in the combined glow of Pluto and Charon, at wavelengths where Earth's own atmosphere absorbs most incoming infrared light. The researchers published their predictions and waited for a telescope powerful enough to put them to the test. Webb was that telescope. And when MIRI measured Pluto's mid-infrared emission, the numbers matched. The haze was glowing exactly as the model had said it would. Organic particles suspended in a near vacuum were absorbing ultraviolet light, heating up, and radiating in the infrared, controlling the temperature of an atmosphere that has no parallel anywhere else we have studied. The lead scientist on the original hypothesis described it as a rare case in planetary science of a theory being so directly and quickly confirmed. But the confirmation of haze-driven cooling was only the start. The full thermal spectrum revealed a far more layered story. Pluto's surface temperature varied as the world rotated, with thermal emission shifting in patterns that trace the distribution of different ices across the globe. Regions rich in nitrogen ice radiated differently from regions rich in methane. The dark reddish-brown thallium-coated terrain absorbed and re-emitted heat in its own characteristic way. Pluto was not one uniform surface. It was a patchwork of chemically distinct zones, each responding to feeble sunlight on its own timescale, each participating in a long, slow exchange of material driven by an orbit that takes 2.5 centuries to complete. And then there was Charon. Webb's ability to separate Charon's thermal signal from Pluto's revealed that the Moon is a very different world. Charon shows no atmospheric signature. Its surface is dominated by water ice mixed with ammonia-bearing compounds, and it lacks the volatile ices that drive Pluto's climate. But its polar regions told a stranger story. They are darker and redder than the rest of the Moon, stained with organic material that has no obvious local source. Webb detected carbon dioxide and hydrogen peroxide on Charon's surface, molecules never confirmed there before. The implication was immediate. Methane molecules escaping from Pluto's weak gravity are drifting across the roughly 19,600 kilometers of vacuum between the two worlds and settling onto Charon's frozen poles. There, ultraviolet sunlight breaks the methane apart, and the fragments slowly assemble into heavier organic compounds. Tholins, the same reddish-brown organic residue found on Pluto itself. Pluto is, in effect, painting its own moon with chemical waste from its atmosphere. It is a one-way chemical conveyor belt across thousands of kilometers of empty space, and as far as we know, no other planet and moon system in the solar system behaves this way. This single detail is enough to dismantle the cute image of Pluto, a world that actively leaks molecules onto a neighbor where those molecules are transformed by radiation into complex organic sludge, is not a harmless snowball. It is a chemically active body operating under conditions most people have never had reason to picture. But the picture goes further still. The mid-infrared spectrum revealed the fingerprint of a climate system whose energy balance is governed not from the bottom up, as on Earth, but from the top down. On our planet, the sun warms the surface warms the air, and convection lifts that heat upward. On Pluto, the surface is so cold and the atmosphere so thin that this mechanism barely functions. Instead, the haze particles high above absorb the small ultraviolet flux the distant sun provides, warm slightly, radiate in the infrared, cool, and sink. New particles forming above them begin the same cycle. The atmospheric energy budget is dictated not by the ground, but by a suspended layer of organic grains. One of the lead researchers on the analysis described it as a genuinely new kind of climate, unique in the solar system. A world where the weather, such as it is made not of water or carbon dioxide or sulfuric acid, but of tiny grains of organic poison drifting through a sky so thin it barely qualifies as an atmosphere. If you had told planetary scientists 50 years ago that the most distant classical world in the solar system would turn out to host a climate system found nowhere else, they would have been skeptical. If you had told them that confirming it would require an instrument that did not yet exist, observing in wavelengths no spacecraft had been able to use from that distance, they would have considered it speculation. But that is what happened. Webb looked at Pluto in a way no one had ever looked before, and the first thing it confirmed is that the dwarf planet's climate runs on a mechanism with no parallel anywhere else we have ever observed. The implications reach further than Pluto itself, because if the haze drives the climate, and if the haze is fed by ultraviolet sunlight, and if Pluto is now moving further from the sun on the long outbound leg of its orbit, then a question follows naturally. What happens to the climate when the input fades? What happens to the atmosphere when the volatile ices on the surface stop sublimating quickly enough to replace what condenses out? The Webb data does not show a world in equilibrium. It shows a world in transition. To get a feel for what that transition means in physical terms, it helps to stand for a moment, in imagination, on Pluto itself. At local noon, you look up and find the sun. It is there, but it does not behave like the sun you know. It does not fill the sky. It does not warm your face. It does not cast crisp shadows. From Pluto's average distance of about 39 astronomical units, where 1 astronomical unit is the distance from Earth to the sun, our star appears as a single brilliant point of light in a sky that remains almost completely black even at midday. It is bright enough to read by, perhaps 250 to 300 times brighter than a full moon seen from Earth, but it delivers almost no warmth. The total solar energy reaching Pluto's surface is roughly 1/1500th of what reaches Earth. Imagine standing in a vast dark cathedral with a single candle burning at the far end of the nave. You can see the flame. You know it is there, but it does not warm the stone beneath your feet. That is the sun, as experienced from Pluto. This is the first physical fact the sentimental image quietly hides. When people see New Horizons photographs of Pluto's surface, they see what looks like a brightly lit landscape with sharp detail. That impression is an artifact of long exposures and image processing. The human experience of standing there would be radically different. The land would appear bathed in a dim bluish twilight. Colors would be muted. The horizon would fade into darkness within a few kilometers. Stars would remain visible in the daytime sky because the atmosphere is far too thin to scatter sunlight into a blue glow the way Earth's does. You would stand in a landscape that is somehow both sunlit and dark at the same time. Now consider the temperature. Pluto's surface hovers between roughly 40 and 60 Kelvin. In Celsius, that is between about -233 and -213 degrees. These numbers are so far below anything humans normally encounter that they lose intuitive meaning. Nothing in ordinary experience comes close. At these temperatures, the familiar categories of solid, liquid, and gas rearrange themselves in ways that defy everyday assumptions. Nitrogen, the gas that makes up 78% of every breath you take on Earth, exists as a solid crystal on Pluto. It forms ice sheets that behave like glaciers, slowly flowing under their own weight. Water, the substance most people associate with cold and ice, is frozen so thoroughly that it becomes as rigid and immovable as granite. Water ice on Pluto is structural bedrock. It does not flow. It does not crack under ordinary stresses. It forms the permanent foundation of the crust, on which softer ices migrate. Methane, the gas that burns in a kitchen stove, freezes into solid crystals on Pluto's highland ridges and peaks. Carbon monoxide, a colorless toxic gas on Earth, solidifies and mixes with the nitrogen ice in the basin floors. Every substance that exists as an invisible gas in Earth's atmosphere becomes a mineral on Pluto. The ground beneath your feet on that world would be made of frozen sky. And the ground does evaporate. That is the volatile cycle the Webb data revealed in action. When the faint sunlight reaches the nitrogen plains, even that trickle of energy is enough to sublimate nitrogen directly from solid to gas. Molecules break free of the crystal lattice, drift upward into the thin atmosphere, travel across the planet, and refreeze in colder, shadowed regions. This is not a metaphor. The ground on Pluto literally evaporates and reforms somewhere else. Pluto's tilt is extreme, around 120 degrees, and its orbit is highly elliptical, swinging from about 30 astronomical units at perihelion to nearly 50 at aphelion. Over the 248 years it takes to complete one orbit, the amount of sunlight reaching the surface varies dramatically. At closest approach, which last occurred in 1989, Pluto receives nearly 3 times more solar energy than at its most distant point. That difference is enough to drive an entire global cycle of ice migration that operates on timescales of decades to centuries. Sputnik Planitia, the great heart-shaped nitrogen basin, acts as a cold trap. It sits at a low elevation where atmospheric pressure is slightly higher and nitrogen condenses more readily. It accumulates nitrogen drifting in from other regions, which is why it remains so smooth and crater-free. Meanwhile, other parts of the surface lose their nitrogen coating and expose darker bedrock or tholin-stained terrain. The surface Pluto presents to the universe at any given moment is a temporary configuration in a cycle that has been running for millions of years. Webb's thermal measurements captured this volatile distribution at work. Different ices have different emissivities and different thermal inertias, which is a measure of how quickly a surface responds to heating. As Pluto rotated during the Webb observations, the thermal brightness varied in irregular ways, with peaks and troughs that corresponded to specific surface types rotating through the field of view. The nitrogen plains responded one way, the methane-rich highlands another, the dark tholin-coated equator another still. The mid-infrared data effectively painted a thermal map of Pluto, recording not only where the ices are but how each one exchanges energy with the environment. Carbon monoxide, the third major volatile, adds another layer. Its volatility falls between that of nitrogen and methane, and it tends to be mixed into the nitrogen-rich plains. Webb's spectral sensitivity was high enough to detect its thermal contribution, showing that it participates in the same global cycle, but with subtly different timing. The picture that emerges is of a world in constant slow transformation. Ices sublimate in one region, drift through the atmosphere, refreeze in another, are buried under fresh deposits, and are exposed again decades later. The Pluto most people picture as a fixed frozen landscape is in fact reshuffling its own surface chemistry on timescales that, while long compared to a human life, are geologically rapid. And then there is the leak to Charon, which deserves to be considered carefully because it really is unique in the solar system. Pluto's atmosphere extends far above the surface. The exabase, the altitude above which a molecule is more likely to escape into space than to collide with another, sits roughly 1,700 kilometers above the ground. Above that level, fast-moving molecules can leave Pluto entirely. Nitrogen is relatively heavy and mostly stays bound. Methane is lighter, and a meaningful fraction escapes. Some of those escaping methane molecules cross the gap to Charon and freeze onto its dark, airless poles. During Charon's long winter, those poles plunge to roughly -258 degrees Celsius, around 15 Kelvin, cold enough to trap nitrogen as a solid. Methane accumulates there. When spring returns and temperatures rise just enough, the lighter ices like nitrogen and carbon monoxide sublimate back into space, but methane, being less volatile, stays behind. Exposed to direct ultraviolet sunlight without an atmospheric shield, the methane is broken apart. The fragments combine into heavier hydrocarbons, then into still more complex compounds, and eventually into the reddish-brown tholins that color Charon's polar caps. Webb's earlier near-infrared spectra had already detected carbon dioxide and hydrogen peroxide on Charon's surface, byproducts of this radiation-driven chemistry acting on ices over geological time. What this means is that Pluto and Charon form a chemical system spanning two worlds. Pluto produces volatiles. Some escape its gravity. Those volatiles cross interplanetary space. They land on Charon. Radiation transforms them into organic compounds that permanently alter the moon's surface. Pluto is slowly and continuously contaminating its own satellite with processed atmospheric waste. It is a one-directional chemical pipeline, running across nearly 20,000 kilometers of vacuum. If you find yourself sitting with the strangeness of that image, that is a fair reaction. It is also the right moment to mention that if you find this kind of careful look at the outer solar system interesting, leaving a like or subscribing makes it considerably easier to keep producing long-form science explanations like this one. With that said, there is more to unpack, because the Webb data also revealed something about the haze itself that further deepens the picture. The haze does not simply sit at one altitude and radiate passively. The thermal observations suggest that the particles participate in a slow vertical circulation driven by their own radiative behavior. During the Plutonian day, ultraviolet photons strike particles high in the atmosphere. The particles warm slightly. As they warm, they radiate more strongly in the infrared and lose energy. The thermal cycle has a small lag. During the warm phase, the particles are slightly more buoyant in the surrounding gas. As they cool and contract, they sink. Meanwhile, new particles form higher up through ongoing photochemistry, and they begin their own cycle of absorption, warming, emission, and descent. The result is a continuous slow circulation of the haze column. It is not convection in the familiar sense, driven by surface heating. It is a radiative circulation driven by individual organic grains responding to the meager pulse of a very distant sun. The atmosphere's thermal structure is shaped, in effect, by the collective behavior of trillions of tiny particles, each one absorbing and ray-emitting photons. This realization landed with real force in the planetary science community. Researchers who study exoplanet atmospheres took immediate notice, because haze-driven climates have been proposed as possible explanations for puzzling observations of small cold worlds around distant stars. If Pluto demonstrates that organic haze can dominate a planetary energy balance under the right conditions, then similar processes may operate on sub-Neptune exoplanets, on small worlds with thin atmospheres, on tidally locked planets that receive only modest stellar radiation. Pluto, the solar system's most famous demoted world, has become a working laboratory for understanding atmospheric physics on planets we may never visit directly. There is also a curious parallel closer to home. Before oxygen rose in Earth's atmosphere roughly 2.5 billion years ago, our own air was rich in methane and nitrogen and had no free oxygen. Under those conditions, photochemistry would have produced organic haze similar in composition to what we see on Pluto and on Saturn's moon Titan. Some researchers have suggested that early Earth was periodically wrapped in organic haze that influenced its surface temperature and shielded the surface from ultraviolet radiation, possibly playing a role in the chemistry that led to life. Pluto offers a present-day natural laboratory for studying how such a haze affects a planetary energy balance. The most distant classical world in the solar system may end up teaching us something about the early conditions on our own. The irony is sharp. The world most people think of as inert and irrelevant may help illuminate how the only known living planet became habitable, but none of this should be confused with comfort. Webb's data does not make Pluto more familiar. It makes Pluto more alien. Every layer of detail pushes the world further from the sentimental image. The haze is not a beautiful blue veil. It is a radiative cooling system made of organic poison that chills the atmosphere into a regime where even nitrogen condenses. The volatile cycle is not a gentle seasonal rhythm. It is a planet-wide redistribution of surface material driven by a sun so faint it appears as a cold, bright star in an almost black sky. The interaction with Charon is not a charming quirk. It is a one-way chemical contamination process that permanently alters a second world. And the question that frames everything still hangs in the air. If Pluto's climate is driven by haze, and the haze is fed by ultraviolet sunlight, and Pluto is now receding from the sun on its long elliptical orbit, what happens next? The Webb data does not show a world in steady state. It shows a world in transition. Pluto's atmosphere reached its maximum extent sometime in the late 20th century, lagging behind the perihelion passage of 1989 because of thermal inertia in the surface ices. Now, as the dwarf planet pulls away from the sun, that maximum is behind us. The atmosphere has begun to change. Ground-based astronomers have monitored Pluto for years using a technique called stellar occultation. When Pluto passes in front of a background star, its atmosphere refracts the starlight in measurable ways. The shape and depth of the dimming pattern reveal the density and structure of the air through which the light passed. These observations show that Pluto's surface pressure dropped from roughly 1 Pascal in 2015, the year of the New Horizons flyby, to about 0.91 pascals by 2020, a decline of around 9% in just 5 years. 9% of a tiny pressure may sound like nothing worth worrying about. But on a world where the atmosphere exists only because the surface ices are just barely warm enough to sublimate, any sustained decline is a signal that the balance is tipping. The atmosphere is not a permanent feature of Pluto. It is a temporary phenomenon sustained only during the relatively brief part of the orbit, when sunlight is strong enough to keep volatile ices in their gaseous state against the cold of space. What happens as Pluto continues to recede is one of the most fascinating unresolved questions in outer solar system science. The leading models predict that as solar input drops, nitrogen sublimation slows, atmospheric pressure declines further, and at some point over the coming decades to centuries, the system crosses a threshold. The atmosphere begins to collapse. Atmospheric collapse on Pluto does not mean a dramatic event. It is not an explosion or a rupture. It is closer to a lake slowly draining through a crack in its own floor. As temperatures drop, the rate at which nitrogen condenses onto the surface exceeds the rate at which it sublimates off. The atmosphere gradually deflates. Pressure falls. The haze thins because there is less methane being lifted into the upper atmosphere to fuel photochemistry. The volatile cycle weakens. Eventually, the atmosphere becomes so thin that it stops functioning as a meaningful gaseous envelope. What remains is a surface-bound frost layer and a nearly perfect vacuum above. The timeline is uncertain. Some models predict the atmosphere will be largely collapsed within a few decades. Others suggest that thermal inertia in the deep nitrogen ice reservoirs of Sputnik Planitia will sustain sublimation longer, possibly maintaining a detectable atmosphere for more than a century even as Pluto moves outward. The answer depends on parameters that are still poorly known, including the total volume of nitrogen available for sublimation, the thermal conductivity of the surface layers, the reflectivity of different ice deposits, and the feedback effects of the haze itself. If the haze cools the atmosphere efficiently, as Webb has now confirmed, it can accelerate the collapse. A colder atmosphere means faster condensation, which means lower pressure, which means less photochemistry, which means less haze production. The feedback loops are tangled and not yet fully resolved. Even before any final collapse, the intermediate stages would transform Pluto in subtle but real ways. As pressure falls, the haze column begins to thin. Haze production depends on ultraviolet photolysis of methane in the upper atmosphere. As the ultraviolet flux drops, less methane is broken apart, fewer organic fragments are produced, and the rate of particle formation slows. The towering haze layer that currently extends more than 300 kilometers above the surface becomes progressively sparser over decades. Fewer particles mean less radiative cooling, which might seem like it should warm the atmosphere, but it also means less ultraviolet absorption, which reduces the energy input that the haze layer captures. The two effects partially cancel. The net result is an atmosphere that is both thinner and less thermally active. The climate engine does not just slow down, it loses parts. The very mechanism that made Pluto's atmosphere unique begins to dismantle itself. On the surface, the consequences would manifest as a gradual shift in the geography of ice. With sublimation slowing, the volatile transport cycle weakens. Sputnik Planitia continues to accumulate material, but at a diminishing rate. Other regions that once lost nitrogen to sublimation begin to retain their coatings for longer. The surface becomes more uniformly frosted as the selective evaporation that created Pluto's striking patchwork of bright and dark terrain slows toward equilibrium. Methane, being less volatile than nitrogen, persists longer. This creates a transitional phase in which Pluto's surface composition shifts. Regions previously dominated by nitrogen ice would become methane-rich as nitrogen sublimates away and is not replenished at the same pace. Spectral signatures change. Reflectivity patterns shift. The familiar geography recorded by New Horizons would gradually become unrecognizable, not because of any dramatic event, but through the slow redistribution of materials. Meanwhile, the slow rain of tholin particles from the haze would diminish. With less haze production, less organic material falls per year. Existing deposits remain, but new deposition slows. Over centuries, the dark equatorial bands stop darkening at the rate they once did. The tholin layer becomes a fossil record of a more active atmospheric era. The most haunting aspect of all this is its silence. There is no dramatic moment. No visible catastrophe marks the change from a world with an atmosphere to a world without one. The transition unfolds in increments too small for any single observation to capture. A fraction of a pascal of pressure lost per decade, a slight thinning of the haze column, a gradual slowing of the ice migration. An astronomer observing Pluto in 2050 would see a world that looks almost identical to the one Webb observed in 2022. By 2100, the differences might be measurable. By 2200, the atmosphere might be undetectable. A late-stage Pluto, in the depths of atmospheric collapse, would be a landscape of extraordinary stillness. No sublimation plumes, no drifting haze, no volatile transport, just ice cold beyond ordinary comprehension, sealed under a vacuum so complete that an individual molecule on the surface would have essentially no chance of encountering another gas phase molecule above it. The nitrogen ice that currently participates in a global cycle would sit motionless, locked in place by temperatures so low that thermal energy is insufficient to free any meaningful number of molecules from the crystal lattice. The surface would not be dead in the biological sense, because it was never alive, but it would be thermodynamically frozen, a system in which nothing moves, nothing changes, nothing transforms until the long orbit eventually carries Pluto back toward the Sun, and the entire cycle begins again. The atmosphere we observe today, in other words, is not a permanent feature of Pluto. It is a seasonal phenomenon on a world where a single season lasts longer than the entire history of Western civilization. The atmosphere inflates near perihelion and deflates near aphelion. We happen to be studying Pluto during the period when its atmosphere is near its maximum extent. Future generations of astronomers may point their telescopes at Pluto and find a world with no detectable atmosphere at all. A frozen globe sealed under a layer of nitrogen ice with nothing above it but vacuum and starlight. That possibility carries a quiet emotional weight. People who grew up with the New Horizons images, who fell in love with the heart-shaped plane and the layered blue haze, may live long enough to learn that the atmosphere responsible for those features has effectively ceased to exist. The haze will be gone. The volatile cycle will have stalled. The leak to Charon will have shut down. The Pluto preserved in those iconic photographs will have become a historical artifact, a portrait of a temporary state the planet itself has long since abandoned. But the possibility of atmospheric collapse is only one dimension of Pluto's physical hostility. To see why deeper observation makes the world feel more alien rather than more familiar, it helps to set Pluto into its broader context. Pluto does not orbit alone. It is the largest known member of a vast population of icy bodies in a region called the Kuiper Belt, which stretches from roughly 30 astronomical units, just inside Neptune's orbit, to approximately 50 astronomical units from the Sun. The belt is estimated to contain more than 100,000 objects larger than 100 kilometers in diameter and billions of smaller bodies, too faint to detect from Earth. For decades, the Kuiper Belt was treated as a kind of cosmic junkyard, a reservoir of frozen leftovers from the formation of the solar system about 4.5 billion years ago. The objects in it were assumed to be inert, geologically dead, chemically simple. Pluto was considered the biggest of these relics. Its demotion from full planetary status in 2006 was driven partly by the recognition that it is one of many similar bodies, rather than a unique world deserving special classification. Webb has begun to take that assumption apart. Webb's near-infrared spectrograph has been surveying trans-Neptunian objects as part of a large program designed to determine their surface compositions. The results, published in 2025, identified at least 3 distinct compositional classes among these worlds, each with different mixtures of ices and organic compounds. Some surfaces are dominated by complex hydrocarbons and methanol. Others are rich in carbon dioxide and lighter organics. Still others show water ice mixed with ammonia-bearing species. The diversity is striking because it suggests these objects are not simple uniform balls of ice but worlds with varied surface histories shaped by radiation processing, volatile loss, and in some cases internal activity. This chemical complexity extends the lesson of Pluto outward across the entire outer solar system. Pluto is not an anomaly. It is the most visible example of a phenomenon that appears to be widespread among icy bodies beyond Neptune. These worlds have surfaces that are chemically active, responding to the thin drizzle of ultraviolet radiation and cosmic rays that reaches them even at enormous distances from the Sun. Their ices are slowly being broken down, rearranged, and combined into new molecules. Organic compounds accumulate on surfaces where temperatures hover only a few tens of degrees above absolute zero. Consider what this means in physical terms. At Pluto's distance, the Sun delivers negligible warmth. At 50 astronomical units, the energy drops to roughly 1/2500th of what Earth receives. And yet at these distances, ultraviolet photons and high-energy cosmic rays continue to arrive, slowly and relentlessly. They drive chemistry on the surface of every exposed body they strike. Methane molecules are shattered. Nitrogen bonds break. Carbon-hydrogen chains accumulate into heavier compounds. Tholins build up. Surfaces darken, redden, and acquire complex organic coatings that transform their appearance and thermal behavior over millions of years. This is radiation chemistry in conditions of almost total darkness. Not the productive chemistry of a warm, wet world. Not the chemistry that leads to life as we understand it. It is the slow, cold, mostly destructive chemistry of a frontier where energy is scarce and molecular transformation happens one photon at a time over geological ages. The products are not biological. They are something closer to the organic equivalent of rust. Complex compounds accumulating on surfaces that no living thing will ever touch. Eris, the most massive known dwarf planet, orbits in the scattered disk at distances ranging from about 38 astronomical units to nearly 98, Its surface is covered in methane and nitrogen. Ice is similar to Pluto's, but brighter, possibly because of fresh frost condensing out of a temporary atmosphere. Makemake shows a surface dominated by methane ice with a reddish tinge from tholin production. Haumea, one of the strangest known dwarf planets, has an elongated shape from a past collision and a surface of crystalline water ice that hints at past internal heating. Each of these worlds presents its own puzzle, its own variation on the theme of frozen volatiles and radiation-driven chemistry. The picture emerging from Webb's survey is not one of dead, uniform ice balls scattered through empty space. It is a picture of a reactive, restless region where surfaces evolve, atmospheres flicker in and out of existence with orbital cycles, and organic compounds accumulate in quantities that were never anticipated before direct spectroscopic observation became possible. Sedna, a distant object whose orbit takes it from roughly 76 astronomical units at its closest to over 900 at its farthest, represents perhaps the most extreme version of this phenomenon. Its surface shows signs of complex organic chemistry, despite spending most of its orbit at distances where solar energy is essentially negligible. Whatever processing occurred on Sedna's surface either happened during rare close approaches or built up through cosmic ray bombardment over billions of years. Either way, the result is not pristine ice, but a chemically altered landscape shaped by long-duration radiation exposure. This broader context matters because it explains why Pluto feels more hostile the more clearly we examine it. Pluto is not an isolated curiosity. It is the flagship of a population of worlds that exist in conditions fundamentally different from anything in the inner solar system. These are places where sunlight barely reaches. Temperatures are measured in tens of Kelvin, and the distinction between atmosphere and surface is blurred because the surface itself is made of substances that could become atmosphere if conditions shifted by even a few degrees. They are worlds where chemistry still happens, not because energy is abundant, but because even a trickle of ultraviolet radiation sustained over billions of years is enough to transform surfaces. Pluto, sitting at the inner edge of this population and receiving the most sunlight of any well-studied Kuiper Belt body, represents the most active and accessible version of these processes. Its haze-driven climate, its volatile ice transport, its leakage to Charon, its potential atmospheric collapse, all of these may occur in attenuated forms on other trans-Neptunian objects. Pluto is the case study. It is the world where these processes are most visible, most measurable, and most directly revealed by Webb's instruments. But visibility does not mean comfort. The more clearly Webb reveals Pluto's environment, the less the dwarf planet resembles the warm mental image people carry. Each new data point pushes Pluto further from familiarity and deeper into a category of physical experience that humans are not built to grasp intuitively. We understand cold, but not 40 Kelvin. We understand thin air, but not 100,000th of an atmosphere. We understand dim light, but not a sun that delivers less heat than a candle at the far end of a long hall. We understand seasonal change, but not seasons that last longer than the Roman Empire. The physical reality of Pluto, as Webb has finally revealed it in thermal and compositional detail, is that the basic environmental conditions are so extreme that the processes governing its surface and atmosphere operate in regimes with no counterpart in human experience. The climate is driven by organic haze. The surface is made of frozen gases that sublimate and refreeze in patterns set by a 2.5-century orbit. The atmosphere itself may be in the early stages of collapsing into ice over the span of a human lifetime. Molecules escape from one world and chemically contaminate another across thousands of kilometers of vacuum. None of this is frightening in the way a horror story is frightening. There is no monster on Pluto. There is no ancient alien artifact. There is no single distilled secret. What there is instead is more difficult to process. A steady accumulation of physical facts that, taken together, reveal a world so strange and so extreme that the comfortable image of Pluto as a harmless frozen underdog becomes impossible to maintain. The outer solar system is not empty. It is not dead. It is not a vacant lot at the edge of a well-lit neighborhood. It is a vast, dark, chemically active frontier where icy worlds undergo transformations driven by processes so slow and so far removed from human timescales that they barely register as change. But they are real, they are measurable, and thanks to Webb, they are now visible for the first time in the wavelengths where the truth of Pluto's thermal environment can finally be read directly. There is a particular kind of discomfort that comes not from learning something frightening, but from realizing that something you thought you understood was never what you believed it to be. It is the discomfort of failed familiarity. You recognize the name, you know the shape, you remember the story, but the more closely you look, the less the thing in front of you resembles the version in your memory. Eventually, you are forced to admit that the comfortable image you carried was a sketch, built from distance, sentiment, and incomplete information. And now that better observation has arrived, the sketch dissolves. What replaces it is something colder, stranger, and harder to accept. That is what Webb has done to Pluto. The process did not happen all at once. It happened in stages, each one peeling away another layer of the familiar image. Each improvement in observational capability made Pluto less comfortable rather than more. When Clyde Tombaugh first identified Pluto in 1930, it was a moving point of light on a photographic plate. Nothing more. It could have been almost anything. A rocky world like Mars, a small gas envelope, a body of any composition. The point of light carried no information about its true nature. It was a name on a map, and the map was almost entirely blank. People filled in the blanks with imagination. Pluto was cold, presumably because it was far away. It was small, presumably because it was faint. Beyond that, everything was projection. For decades, Pluto existed in the public imagination as a vague, harmless, distant world. The ninth planet, the little one at the end of the list. Hubble provided the next stage. By the 1990s and early 2000s, it could resolve Pluto as a tiny disk with blotchy markings. Hints of complexity, but not enough to interpret in detail. Pluto remained vague, still distant enough to be whatever people wanted it to be. Then New Horizons arrived in 2015 and the image changed dramatically. Suddenly Pluto had a face. It had mountains, plains, and a heart-shaped feature that the world fell in love with. It had layered blue haze that made it look ethereal. The photographs were so vivid that they created a new version of Pluto in the public consciousness. Not the vague dot of earlier decades, but a specific, recognizable world with personality. People put the heart on shirts. They used the images as wallpapers. Pluto became, paradoxically, more beloved after its reclassification than it had ever been as a planet. But embedded in those beautiful images were details that, examined closely, told a far less charming story. The heart-shaped plane was not a symbolic gesture. It was a basin filled with convecting nitrogen ice, churning slowly under its own weight, resurfacing the floor every few 100,000 years. The mountains were not picturesque alpine peaks. They were blocks of water ice so cold they acted like stone. The dark equatorial bands were coatings of organic tholins, the slow product of ultraviolet radiation breaking apart atmospheric methane. The blue haze was not a sky in any human sense. It was a suspended column of organic particles in an atmosphere so thin that standing under it would feel indistinguishable from standing in vacuum. You would feel no air. You would hear no sound. You would not see blue above you. The haze is visible only when backlit by the sun, in specific viewing geometries. Every detail taken seriously moved Pluto further from the familiar. But because the visible images were so compelling, most people stopped at the surface impression. They saw the heart. They saw the blue. They formed an emotional attachment to a version of Pluto that the data never really supported. Webb completed what New Horizons began, not by capturing prettier images, but by looking at Pluto in wavelengths that reveal physical processes rather than scenery. There is no heart in the infrared. There is no iconic blue haze. There is a thermal signature showing how volatile ices migrate across the surface. There is an atmospheric emission spectrum confirming that organic particles cool the air through a process found nowhere else in the solar system. There is a chemical conveyor belt carrying processed atmospheric waste onto the poles of a neighboring moon. There are declining pressure measurements, suggesting that the atmosphere captured in those famous photographs may be in the early stages of freezing onto the ground. This is what it means in the sober sense to call the situation horrifying, not a monster, not a jump scare, the progressive dissolution of a familiar image under the pressure of better observation. Every improvement in how we see Pluto makes the world harder to emotionally accept, not easier. The closer we look, the less Pluto resembles the version of itself that lives in popular imagination. The more clearly it becomes something cold, strange, and genuinely difficult to fit into ordinary categories of thought. This is an unusual kind of scientific discomfort. Normally, better observation makes things clearer and more manageable. You study a disease and learn to treat it. You map a genome and understand how an organism functions. You photograph a distant galaxy and place it in a taxonomy of known structures. Understanding reduces fear. The unknown becomes known and the known becomes safe. Pluto reverses this process. Every new observation makes it less safe, less domestic, less recognizable. The discovery of its geological complexity did not make it feel like a familiar rocky world. It revealed processes operating under conditions no rocky world experiences. The detection of its haze did not make it feel like it had a sky. It revealed an atmospheric cooling mechanism that operates by rules alien to every other atmosphere studied. The confirmation of volatile transport did not make it feel like it had weather. It revealed a surface that literally evaporates and reforms on timescales tied to an orbit lasting 2.5 centuries. Each finding is individually fascinating. Taken together, they compose a portrait of a world that resists every attempt to make it feel ordinary. And this is where a deeper discomfort settles in. Pluto is not an obscure object at the fringes of detection. It is one of the most culturally familiar bodies in astronomy. Everyone knows its name. Everyone has an opinion about whether it should be called a planet. Everyone remembers learning the list of planets as a child and placing Pluto at the end as the smallest and most distant member of the family. Pluto occupies a specific emotional location in the mental maps of billions of people. It is the underdog, the misfit, the lovable outcast. Webb reveals that the outcast is not lovable. It is alien. And the gap between the cultural image and the physical reality is so wide that bridging it requires letting go of nearly a century of accumulated emotional associations. That gap matters beyond Pluto. It says something about how humans construct mental models of the cosmos and how stubbornly those models resist revision. Most people carry a picture of the solar system assembled in childhood and rarely updated. A neat arrangement of named bodies on tidy concentric paths. Mars is red, Jupiter is stormy, Saturn has rings. Beyond Neptune there is Pluto, small and cold. Beyond that nothing, empty space, the end. That picture is not just oversimplified. It is structurally wrong. It treats the solar system as a tidy, well-lit neighborhood where everything has been explored and named. The reality is radically different. The region inside Neptune's orbit, the part that contains all 8 planets, all the named worlds, all the missions and photographs, represents a tiny fraction of the Sun's gravitational domain. The Kuiper Belt alone occupies a volume far larger than the planetary region. The scattered disk extends much farther. The hypothetical Oort cloud, if it exists as theorized, may stretch to 100,000 astronomical units, nearly halfway to the nearest star. In other words, everything most people think of as the solar system, all the planets, all the moons, all the missions, all the history, is confined to the well-lit entryway of a structure that extends into darkness for distances that dwarf the familiar neighborhood by factors of thousands. The solar system is a house in which humanity has explored only the rooms near the front door. Beyond those rooms, corridors stretch into unlit wings we have barely glimpsed, populated by icy bodies in quantities we can only estimate, undergoing chemical and physical processes we are just beginning to detect. Pluto sits at the threshold between the known and the unknown. It is the last named world most people recognize before the outer darkness begins. Webb's observations reveal that even this threshold world, this most familiar representative of the outer system, operates under conditions so extreme that they defy easy comprehension. If Pluto is this strange, what are the thousands of unnamed Kuiper Belt objects like? What conditions prevail on worlds orbiting at 50, 60, 80 astronomical units, where sunlight is so faint that temperatures drop to 30 Kelvin and below? What chemistry occurs on the surfaces of objects in the scattered disk, bombarded by cosmic rays for billions of years in near total darkness? The honest answer is that we do not fully know. Webb's survey of trans-Neptunian objects has begun to map their surface compositions, but compositional classification is only the beginning. Understanding the physical processes on these worlds, their climates, their atmospheric behavior, their volatile cycles, will require sustained observation over decades. Pluto, the best-studied member of this population, took nearly a century to reach the level of understanding Webb has now provided. Even that understanding is incomplete, contested, and evolving. What Webb has accomplished is not a final answer about Pluto. It is a demonstration of what happens when a genuinely powerful instrument is pointed at a world previously known only through glimpses. The result is not resolution. It is deeper complexity. More questions, not fewer. More strangeness, not less. The data do not simplify Pluto. They reveal layers of physical behavior that make the world progressively harder to fit into any comfortable category. This is perhaps the most important insight that emerges from the entire story. The impulse to categorize Pluto, to call it a planet or a dwarf planet, to assign it a rank in some hierarchy, to decide whether it is important or unimportant, is a fundamentally human impulse. We want to organize the cosmos into comprehensible units. We want to know where things fit. Pluto resists that organization. It is not a planet in the classical sense. It is not an asteroid. It is not a comet. It is not a moon. It is a dwarf planet, a category invented specifically to accommodate objects that did not fit anywhere else. And even within that category, Pluto is anomalous. The largest by volume, the only one with a confirmed atmosphere, the only one with a known haze-driven climate, the only one observed to chemically contaminate its own moon. Pluto is the solar system's most famous misfit, and Webb has revealed that its misfitting runs far deeper than taxonomy. The real shock is not that Pluto was reclassified. The real shock is that the more we learn about its physical reality, the more we realize our categories were never adequate to describe what this world actually is. Pluto is not a small planet that failed to clear its orbit. It is a large, chemically active, climate-driven icy world at the inner edge of a vast population of similar bodies, operating under conditions that make it more alien than Mars, more dynamic than Mercury, and more unsettling than most of the moons of the giant planets, despite being smaller than any of them. This realization challenges the implicit hierarchy most people carry in their heads. In the standard mental model, size equals importance. Jupiter matters because it is large. Earth matters because we live on it. Pluto does not matter because it is small and far away. Webb's data dissolves that assumption. Size tells you almost nothing about physical complexity or scientific interest. Pluto's haze-driven climate is unlike anything on Jupiter. Its volatile ice cycle is more chemically intricate than any process active on Mars today. Its atmospheric leak to Charon has no analog among the giant planet-moon systems. Smallness and distance did not make Pluto simple. They made it overlooked. And being overlooked allowed the sentimental image to persist unchallenged for decades. People could believe Pluto was a harmless snowball because nobody had the tools to show them otherwise. They could project warmth onto a world they had never truly seen because the incomplete data left room for emotional interpretation. The heart-shaped feature became a symbol onto which people mapped their feelings about cosmic injustice. The actual physical reality of that feature, nitrogen ice convecting in a basin possibly formed by an ancient impact, was largely irrelevant to the emotional narrative. Webb makes that narrative untenable. not by dramatically refuting it, but by filling in the physical details so thoroughly that the sentimental version can no longer coexist with the scientific one. You cannot simultaneously believe that Pluto is a cute, harmless outcast, and that it is a world where organic haze cools the atmosphere through a process found nowhere else, where the surface sublimates and migrates across the globe over centuries, where atmospheric methane escapes across thousands of kilometers of vacuum and is chemically transformed into organic sludge on a neighboring moon, and where the atmosphere itself may be in the early stages of freezing solid. Both versions of Pluto cannot occupy the same mental space. One is a comfort, the other is a fact. Webb forces the choice, and the fact is harder to sit with. It is harder because it removes the emotional buffer that distance and ignorance once provided. When Pluto was a dot, it could be anything. When it was a photograph, it could be beautiful. Now that it is a thermal spectrum, a volatile transport model, a declining pressure measurement, and a confirmed haze climate interaction published in peer-reviewed journals, it is what it is. And what it is a world that operates in conditions so far outside human experience that calling it horrifying is not sensationalism. It is closer to understatement. To appreciate just how unlikely it is that we know any of this at all, it helps to remember the chain of accidents and deliberate choices that brought Pluto into focus in the first place. The world was not found because anyone expected it to be what it actually is. It was found because of a mathematical mistake. In the late 1800s and early 1900s, astronomers analyzing the orbits of Uranus and Neptune believed they were detecting small irregularities. Something, they thought, must be tugging on those giant planets from farther out. Percival Lowell, the wealthy American astronomer who had built an observatory in Arizona to search for life on Mars, became obsessed with finding the responsible body. He calculated where it should be and set astronomers to work scanning the sky. He died in 1916 without ever finding it. The search resumed years later, and in 1930, the young assistant Clyde Tombaugh identified a moving point of light that fit the predicted region of sky. It later turned out that the supposed orbital irregularities of Uranus and Neptune had been measurement errors. There was no large hidden planet pulling on them. Pluto, when its true mass was eventually determined, turned out to be far too small to perturb the giant planets at all. Pluto was found because astronomers were searching in roughly the right area of sky for the wrong reason. The discovery was almost a coincidence dressed up as a prediction. This origin story matters because it shaped how Pluto was treated for the next 76 years. Having been discovered as the result of a planetary search, it inherited the title of planet by default. Its actual size, mass, and composition were almost entirely unknown for decades after its discovery. Estimates of its mass were repeatedly revised downward as observations improved. In 1931, just a year after the discovery, Pluto was assumed to be roughly the mass of Earth. By 1948, that estimate had dropped to about the mass of Mars. By 1976, it was estimated at 1% of Earth's mass. After the discovery of Charon in 1978 allowed astronomers to calculate the combined mass of the system directly, Pluto's true mass was determined to be only about 0.22% of Earth, roughly 1/500th of our planet's mass. Each downward revision of Pluto's size pushed it further away from the company of the major planets and closer to the population of small icy bodies that astronomers were beginning to suspect must exist beyond Neptune. The existence of such a population had been hypothesized as early as the 1940s by astronomers Kenneth Edgeworth and Gerard Kuiper, who reasoned that the disk of debris from which the solar system formed should not simply end at Neptune. There should be a reservoir of leftover icy bodies extending farther out. Confirmation came slowly. The first additional trans-Neptunian object beyond Pluto and Charon was not discovered until 1992, when astronomers David Jewett and Jane Liu found a small icy body now known as 1992 QB1. Within a few years, dozens more were identified. By the early 2000s, hundreds were known. Today, more than 3,000 trans-Neptunian objects have been cataloged, and the true population is estimated to number in the hundreds of thousands. The discovery of these objects forced a slow reconsideration of Pluto's status. As more bodies similar in size and composition were found, it became increasingly difficult to justify treating Pluto as fundamentally different from the rest of the population. The breaking point came in 2005 with the discovery of Eris, an object initially thought to be larger than Pluto. Faced with the question of whether to call Eris the 10th planet or to reconsider the definition of planet entirely, the International Astronomical Union took up the issue in 2006. After contentious debate, the Union adopted a definition that required a planet to have cleared its orbital neighborhood of other bodies. Pluto, sharing its orbital region with countless other Kuiper Belt objects, did not meet that criterion. It was reclassified as a dwarf planet. The decision was scientifically defensible but emotionally fraught. The public reaction was unusually intense for what was, in essence, a matter of nomenclature. People felt protective of Pluto. Editorials were written. Petitions were signed. The reclassification became a cultural touchstone, repeated in jokes, songs, and films. The sentiment around Pluto deepened precisely because the world had been demoted. It became a symbol of cosmic underdogs, of victims of bureaucratic decisions, of the small thing that did not deserve what happened to it. All of this emotional weight, accumulated over decades of incomplete knowledge, is what Webb's data now collides with. The reclassification debate, in retrospect, focused on the wrong question. The interesting thing about Pluto was never whether it should be called a planet. The interesting thing is what it is physically. And what it is physically, as we are only now beginning to understand, is a world that does not fit any of the categories we have been arguing about. Calling it a planet or a dwarf planet does not describe its haze-driven climate, its sublimation cycle, its chemical interaction with Charon, or its possible internal ocean. The labels are administrative. The world is something else entirely. It helps, too, to put Pluto into context by comparing it with two other worlds that share certain features but illustrate how different the outcomes can be. The first is Triton, the largest moon of Neptune. Triton is similar in size to Pluto, only slightly larger, with a comparable density and a surface composed largely of nitrogen, methane, and carbon dioxide ices. Voyager 2 flew past Triton in 1989 and revealed a world that, like Pluto, has a thin nitrogen atmosphere, an active surface, and even erupting geysers of nitrogen gas. But Triton is captured. It orbits Neptune in the opposite direction of the planet's rotation, a backward orbit that indicates Triton did not form where it now resides. It almost certainly originated in the Kuiper Belt and was gravitationally captured by Neptune billions of years ago. In other words, Triton is what Pluto might have become if Pluto had ever drifted too close to a giant planet. The two worlds may share a common origin, but they followed wildly different paths. The comparison sharpens what is unique about Pluto. Triton's atmosphere is even thinner than Pluto's. Its haze is far less developed. Its surface activity is driven partly by tidal heating from Neptune and partly by seasonal sublimation. Pluto, free of any captured relationship with a giant planet, retains its own independent dynamics. Its atmosphere is fed not by tidal stress but by its long elliptical orbit. Its haze is supported by the slow rhythm of perihelion and aphelion. The processes shaping Pluto's surface are intrinsic to it, not imposed from outside by a more massive neighbor. The second comparison is Titan, Saturn's largest moon. Titan is much larger than Pluto and has a far denser atmosphere, more than 1.5 times the surface pressure of Earth, dominated by nitrogen with significant methane. Titan also has a thick organic haze that gives it an orange color and shrouds its surface from optical view. At first glance, this might seem to resemble Pluto's haze, but the physics is fundamentally different. Titan's atmosphere is dense enough that gas phase chemistry and convection dominate its climate. Its haze contributes to the energy balance, but it is not the dominant driver. Pluto sits in a different regime, where the atmosphere is so thin that gas phase processes are weak, and the haze ends up controlling the temperature structure by default. Together, Triton, Titan, and Pluto define a sort of spectrum. Titan has a thick atmosphere and a dense haze that complements gas phase climate physics. Pluto has a thin atmosphere where the haze takes over the role of primary climate regulator. Triton has an even thinner atmosphere where neither gases nor haze dominate, and tidal heating provides the energy that drives surface activity. 3 worlds, 3 different solutions to the problem of what happens when nitrogen ice meets ultraviolet light at extreme cold. There is also a more subtle process operating on all of these worlds that is worth pulling into the picture. Cosmic rays, the high-energy particles produced by distant supernovae and accelerated through the galaxy, continuously bombard every exposed surface in the solar system. Inside the inner solar system, the sun's magnetic field deflects most of these particles. In the outer solar system, where solar protection weakens, cosmic rays reach the surface with significant flux. On worlds without atmospheres like Charon, cosmic rays directly process the surface ice, breaking bonds, generating radicals, and producing new molecules over geological time. On worlds with thin atmospheres like Pluto, cosmic rays contribute to upper atmospheric chemistry, helping to drive the formation of complex organics in regions where ultraviolet light alone would not be sufficient. This means that even if Pluto's atmosphere collapses entirely during its long aphelion phase, the surface will not become chemically inert. Cosmic ray bombardment will continue. New tholins will continue to form, just at a slower rate. Existing tholins will be further transformed by ongoing radiation processing. The surface chemistry will not stop. It will simply shift to a slower mode, driven by background radiation rather than active ultraviolet photochemistry in an extant atmosphere. The same processes are believed to operate on every exposed icy body in the outer solar system, on the Kuiper Belt objects, on the centaurs, and even on the hypothetical bodies of the Oort cloud. Every icy surface in the cold, dark reaches of the solar system is slowly being chemically altered. Over billions of years, the cumulative effect is enormous. The reddish coloration observed on many trans-Neptunian objects, the variations in their spectra, the differences in their surface compositions. All of these are at least partly the result of cosmic ray and ultraviolet processing operating across geological time. Pluto, then, is not just a single strange world. It is the most accessible example of a process that is happening across an enormous region of the solar system. Studying Pluto in detail teaches us about an entire population of bodies that we may never visit individually, but whose collective behavior shapes the chemical inventory of the outer solar system. This brings the question of how Webb actually accomplished its measurements back into focus, because the engineering involved is itself extraordinary and worth understanding. Detecting the thermal emission of Pluto in the mid-infrared from Earth's vicinity is not easy. The signal is extraordinarily faint. Pluto is so cold that the peak of its blackbody emission lies near 20 to 25 micrometers, in a part of the spectrum where Earth's own atmosphere absorbs almost all incoming light. Ground-based telescopes simply cannot make these measurements. Even space-based observatories struggle, because their own instruments emit infrared light at room temperature, which would drown out the faint signal from Pluto. Webb solves this problem by being extremely cold. The telescope's primary mirror operates at around 50 Kelvin, only 10 Kelvin warmer than Pluto's surface. The mid-infrared instrument is cooled even further, to about 7 Kelvin, using a dedicated cryocooler. At those temperatures, the telescope itself emits almost no infrared light, allowing it to detect the faint thermal signal from a distant cold body without being overwhelmed by its own glow. Achieving and maintaining those temperatures in space, hundreds of thousands of kilometers from Earth, required engineering of remarkable precision. Webb's sunshield, a 5-layer structure roughly the size of a tennis court, blocks heat from the sun, Earth, and Moon, allowing the telescope to passively cool to its operating temperature. The active cooling of the mid-infrared instrument is sustained by a closed-cycle helium cooler designed to run for the lifetime of the mission. Without these capabilities, the mid-infrared observations of Pluto would not be possible. The thermal signal of the haze, the surface temperature variations across the globe, the separation of Pluto's emission from Charon's. All of it required a telescope colder than the worlds it was studying. Webb did not just point at Pluto. It became cold enough to see Pluto in the first place. It is also worth noting that ground-based stellar occultation measurements, the technique used to track Pluto's atmospheric pressure decline, are themselves a remarkable example of how much can be learned from a distance. When Pluto passes in front of a background star, observers on Earth see the starlight dim as it passes through Pluto's atmosphere. The exact shape of the dimming curve depends on the density profile of the atmosphere, the presence of haze layers, and the refractive properties of the gas. By recording these occultations from multiple sites on Earth simultaneously, astronomers can reconstruct the atmospheric structure at the time of the event. Stellar occultations of Pluto are rare. They require a chance alignment between Pluto, a sufficiently bright background star, and an observing site on Earth. Astronomers have learned to predict these events years in advance and to mobilize networks of observers, sometimes including airborne telescopes flown to remote locations, to capture them. The combination of these ground-based occultation measurements with Webb's thermal observations and the New Horizons flyby data gives scientists a multi-dimensional picture of Pluto's atmosphere. Each technique contributes something the others cannot. The occultations track pressure over time. New Horizons provided detailed geometry and composition at a single moment. Webb provides ongoing thermal and spectral monitoring. Together, they describe a world in transition, with a richness that no single observation could provide. This is how modern planetary science works, not through single dramatic discoveries, but through the slow accumulation of complementary measurements that, taken together, reveal the structure of worlds we cannot visit directly. Pluto, in particular, has benefited enormously from this approach. A world that, 50 years ago, was barely more than a dot is now one of the better characterized small bodies in the solar system. Not because anyone built a single grand experiment to study it, but because dozens of independent efforts, from telescope upgrades to occultation networks to a daring spacecraft flyby to a generation-defining space telescope, each contributed a piece. And the picture they have collectively assembled is, as we have seen, profoundly different from the cute frozen underdog of popular imagination. Consider once more the full picture Webb has assembled, a world smaller than Earth's moon, orbiting a sun that appears as a brilliant point in an otherwise black sky. Surface temperatures between -233 and -213 degrees Celsius. A surface made of frozen nitrogen, methane, and carbon monoxide. The very gases that compose breathable atmospheres on other worlds are locked here into ice harder than stone. An atmosphere so thin it qualifies as a vacuum by any engineering standard, yet thick enough to support a towering column of organic haze that controls the planet's climate through radiative cooling. A volatile cycle that causes the surface itself to evaporate and refreeze in shifting patterns over decades and centuries. Atmospheric molecules escaping the planet's weak gravity, drifting across 19,600 kilometers of vacuum, and settling onto the poles of a tidally locked moon, where ultraviolet radiation transforms them into complex organic tar. An atmosphere that may be in the early stages of collapsing entirely, freezing out of existence over the coming decades to centuries, as the world recedes from its distant sun on an orbit lasting 248 years. This is not the description of a harmless object. This is the description of one of the most physically extreme environments in the solar system, a place where every fundamental condition of existence, temperature, pressure, light, chemistry, atmospheric stability, occupies a regime so far beyond human experience that we lack the intuitive vocabulary to describe it without reaching for analogies that quickly break down. And the most unsettling part is that Pluto is not unusual within its own neighborhood. It is typical. It is the largest and best-studied member of a population of thousands of similar bodies occupying the outer solar system, a region that constitutes the vast majority of the Sun's gravitational domain. If Pluto, the most famous and accessible of those worlds, turns out to host a climate system unlike anything found elsewhere, a volatile cycle of extraordinary complexity, and an atmospheric interaction with its moon that has no known parallel. What might the thousands of unstudied Kuiper Belt objects reveal when instruments powerful enough to characterize them finally exist? The answer almost certainly is more strangeness, more complexity, more processes operating in regimes that challenge current models, more evidence that the outer solar system is not the dead frozen wasteland the standard mental model imagines, but a chemically active frontier where icy surfaces evolve, atmospheres flicker in and out of existence with orbital cycles, and organic compounds accumulate in the near-total absence of warmth and light. Percival Lowell, the astronomer who initiated the search for a ninth planet in the early 20th century, called the hypothetical object Planet X, he imagined a large, distant world whose gravity perturbed the orbit of Neptune. He was wrong about almost everything. The perturbations he tried to explain turned out to be measurement errors. The planet he predicted, in the form he imagined, did not exist. Pluto was found in the right region of sky partly by coincidence, and it turned out to be far smaller and far stranger than anything Lowell had anticipated. But Lowell was right about one thing, even if he did not know it. There was something out there beyond the familiar planets, beyond the well-lit rooms of the inner solar system, something that would resist easy comprehension, something that would become more disturbing the more closely it was examined. Webb has given us the clearest look so far at what that something actually is. The truth it reveals is not that Pluto harbors some hidden terror. The truth is quieter, and in its own way more difficult to accept. Pluto is a real place, a physical environment with measurable temperatures, pressures, compositions, and dynamics. A world governed by chemistry and physics that operate at extremes that make it genuinely inhospitable, in ways the cultural image of Pluto has never acknowledged. The unsettling element is not that Webb found a monster. It is that the more seriously Pluto is observed, the less it resembles the harmless little outcast of popular imagination, and the more it becomes what it always was beneath the sentiment: a cold, chemically active, barely sunlit world whose atmospheric and surface behavior quietly destabilize the comfortable mental picture of a solar system that ends neatly at Neptune. Pluto does not become less strange when seen more clearly. It becomes more so, not because it threatens us, not because it harbors danger in any conventional sense, but because it forces a confrontation with a version of physical reality that the human mind is not built to find comfortable. A world where the air freezes and falls as snow, where the ground evaporates and reforms somewhere else, where the sky is made of organic poison drifting through a near vacuum, where the sun is a cold point of light that cannot warm the landscape it illuminates, where even the atmosphere, the most basic prerequisite for a world that feels alive, may be a temporary visitor that comes and goes with seasons lasting longer than civilizations. And yet, the same data that makes Pluto feel more alien also makes it more scientifically valuable than it has ever been. Because once you stop expecting Pluto to be cute and start treating it as a working physical system, the unsolved questions become genuinely interesting. Several major questions remain open. The first concerns the long-term fate of the atmosphere. The pressure decline measured between 2015 and 2020 was clear, but the rate of further decline is uncertain. Will the atmosphere collapse within decades, or will the deep nitrogen reservoir of Sputnik Planitia continue to sublimate for more than a century, supported by stored thermal energy in the ice? Repeated Webb observations over the coming years will be critical. By measuring the thermal spectrum at different points in Pluto's slow recession from the Sun, scientists can directly track how the haze, the surface temperatures, and the atmospheric structure change. For the first time, we will be able to watch a planetary climate transition in something close to real time. A second open question concerns the haze itself. We now know it cools the atmosphere. We do not yet know precisely how the particles form, how their composition varies with altitude, how their grain sizes evolve as they descend, and how efficiently they sediment onto the surface as a function of orbital phase. Laboratory experiments on Earth, in which scientists simulate Pluto-like conditions inside vacuum chambers and irradiate methane and nitrogen mixtures with ultraviolet light, are helping to characterize the chemistry. But matching laboratory tholins to the real particles in Pluto's atmosphere is an ongoing effort. The composition of the haze is still being unpacked, molecule by molecule. A third question concerns the interior. New Horizons observations and subsequent modeling suggested that Pluto may host a subsurface liquid water ocean beneath the rigid water ice crust. The evidence is indirect. Surface features: the apparent positive gravity anomaly of Sputnik Planitia, the geological youth of certain regions, and the persistence of an extensional tectonic pattern across the globe all hint at a deep liquid layer kept warm by residual radioactive heat and possibly antifreeze compounds like ammonia dissolved in the water. If that ocean exists, Pluto joins a growing list of outer solar system bodies, including Europa, Enceladus, Titan, Triton, and possibly several large Kuiper Belt objects that may host hidden internal seas. Webb cannot directly probe these interiors, but its observations of surface composition and thermal behavior help refine the models that try to estimate how much liquid water might still exist deep below the surface of Pluto, and whether any of the chemistry from that interior occasionally reaches the surface. A fourth question concerns Charon. The reddish polar caps, the detection of carbon dioxide and hydrogen peroxide, and the slow accumulation of organic material from Pluto's escaping atmosphere all point to a moon shaped over geological time by chemistry imported from its companion. How long has this transfer been operating? Has it been steady, or has it varied with the orbital evolution of the Pluto-Charon system? What is the total mass of organic material deposited on Charon over 4.5 billion years? Future observations, including potential mission concepts that have been proposed but not yet funded, could begin to answer these questions. A fifth question is whether Pluto is truly representative of larger Kuiper Belt objects. Webb's broader survey of trans-Neptunian objects suggests that there are at least 3 compositional families among these bodies, but Pluto's combination of size, surface activity, and atmospheric behavior is unique within the sample so far. Eris is comparable in size, but has a different reflectivity and possibly a different volatile inventory. Makemake and Haumea each show their own peculiarities. The deeper question is whether haze-driven climates are common among icy worlds with thin nitrogen atmospheres, or whether Pluto is an outlier whose specific orbital and compositional conditions produced a phenomenon that does not appear elsewhere. Resolving this will require both more Webb observations and, eventually, dedicated missions to other trans-Neptunian objects. A sixth question, perhaps the most far-reaching, concerns what Pluto can teach us about planets around other stars. Many of the small exoplanets detected by surveys like Kepler and TESS are likely to be cold worlds with thin atmospheres. Some may have organic hazes generated by photochemistry. Models built to interpret their spectra need realistic examples of how such hazes affect climate. Pluto is the first world where a haze-driven climate has been directly confirmed by thermal observation. Every refinement of the Pluto haze model improves our ability to read the atmospheres of distant worlds we will never visit. This is the quieter, more durable significance of the Webb observations. They do not just rewrite our understanding of one small body. They open a new chapter in how we think about cold worlds in general, both inside and outside the solar system. There is also a more philosophical thread worth pulling. For most of human history, the outer reaches of the solar system existed almost entirely in the imagination. We populated them with myths, with hypothetical planets, with vague ideas of darkness and cold. The first true measurements of those regions, beginning with the discovery of Pluto in 1930 and accelerating through the Voyager era and the New Horizons flyby, gradually replaced imagination with data. Webb represents the next step in that replacement. It is now possible to study the chemistry, climate, and surface dynamics of objects more than 5 billion kilometers away with a precision that, a generation ago, would have been considered fantasy. And what those measurements consistently show is that the universe is stranger than the categories we built to describe it. Pluto is not a planet. It is not just a dwarf planet either, not in the simplified sense the term suggests. It is something else, a world that operates by its own physics, a laboratory for atmospheric processes that have no terrestrial analog, a chemical system spread across two bodies linked by leaking molecules and slow radiation chemistry. A world whose familiar name conceals a deeply unfamiliar reality. If the broader lesson of Webb's Pluto observations had to be summarized in a single line, it would be this: Pluto is more interesting, more active, and more physically extreme than the cultural image has ever suggested. The story of Pluto is not the story of a demoted planet defending its honor. It is the story of a world whose true nature has only just begun to come into view, and whose strangeness reaches further than we expected each time we look more carefully. Pluto is still out there right now, drifting through the outer darkness on an orbit that will not bring it back to its closest approach to the Sun for another 2 centuries. Its haze is still glowing faintly in the infrared. Its volatile ices are still migrating across the surface. Methane is still escaping toward Charon. The atmosphere may still be slowly declining, molecule by molecule, toward the point where it ceases to exist in any meaningful sense. The James Webb Space Telescope, the most powerful observatory ever built, is still watching, still measuring, still revealing details about this world that no human eye will ever directly see, but that no honest account of the solar system can afford to ignore. The universe does not owe us a landscape we can emotionally process. It offers reality instead. And Pluto, seen clearly at last, is one of the coldest, strangest, and most quietly disorienting realities the solar system contains. Not because it is far away, not because it is small, but because it is real, and reality at the edge of the sun's reach looks nothing like the picture we drew when we could not yet see it clearly enough to know. The next time you look up at a clear night sky, somewhere out there beyond the planets you can see, beyond the constellations you can name, beyond the distance that telescopes can resolve from your backyard, that world is turning slowly on its axis. Its atmosphere is glowing in wavelengths the human eye cannot perceive. Its ground is evaporating and reforming itself. Its haze is cooling air that almost is not there. Its moon is being painted by chemistry imported across the void. And on Earth, in laboratories and observatories and quiet rooms full of computers, scientists are still reading the data that Webb continues to return, piecing together the story of a world that, until very recently, no instrument had ever truly seen. That ongoing investigation, more than any single dramatic detail, is the real legacy of the Webb observations. We finally have the tools to understand worlds like Pluto on their own terms, rather than through the filters of distance and sentiment. The picture we are assembling is not always comforting, but it is real, and it is changing how we think about the dark frontier that begins where Neptune ends and stretches into a region that, for all our centuries of astronomy, we are only now starting to map in earnest. If anything in this look at Pluto sparked your curiosity, leaving a like or subscribing makes it considerably easier to keep producing long-form science explanations like this one. There is a great deal more to say about the outer solar system, about the icy worlds beyond Neptune, about the chemistry of cold places, and about what Webb is likely to find next as it continues to scan a frontier that turns out to be far more active, far more chemically intricate, and far stranger than any of us were taught to expect. For now, Pluto remains where it has always been, far, cold, slowly turning, quietly transforming, a world finally beginning to reveal itself to instruments capable of seeing it as it truly is rather than as we once imagined it to be. The next time someone mentions Pluto in passing, perhaps in the context of a list of planets or a piece of trivia or a joke about its reclassification, it may be worth pausing to remember what Webb has shown. Behind the name lies a real place, a landscape of frozen nitrogen and methane, a sky filled with organic haze that controls a climate by radiating heat into space, a moon being chemically painted by molecules that escaped from a neighboring atmosphere, a pressure measurement taken from telescopes on Earth, that is slowly drifting downward as the world recedes from a sun that barely warms it. A thermal spectrum, captured by a telescope cooled almost to the temperature of the world it is studying, that confirms a theory proposed by scientists who guessed correctly about a mechanism nobody had ever directly observed. Behind the name lies a system in motion, a volatile cycle older than human civilization, a chemistry running on photons that traveled nearly 5.5 hours from the sun, a surface evaporating in one place and condensing in another, a world whose seasons unfold on timescales longer than the recorded history of every human language combined. And behind all of that lies the larger lesson. The solar system we learned about as children is a heavily simplified sketch. The real solar system is vastly more complex, more chemically active, and more physically extreme than the tidy diagrams in textbooks suggest. The inner planets are only the beginning. Beyond Neptune lies a region containing more individual worlds than the entire inner solar system, each shaped by processes we are only starting to understand. Pluto is the first of these worlds to be studied in real detail. It will not be the last. There is something quietly humbling about all of this. The universe does not arrange itself for our convenience. It does not provide landscapes that are easy to picture or temperatures that are easy to imagine or chemistry that obeys our intuitions. It offers what it offers, and our job is to look carefully enough to see it. Webb has looked carefully at Pluto, and what it has shown us is a world that, by any honest standard, is one of the most exotic environments within reach of our instruments. We will keep looking. Webb will continue to observe Pluto and the broader Kuiper Belt over the coming years. Ground-based occultation networks will continue to track the atmosphere. Theorists will continue to refine the models of haze chemistry, volatile transport, and possible interior oceans. New mission concepts are already being discussed, including proposals for an orbiter that would spend years studying Pluto rather than mere hours. None of these efforts is guaranteed, but the scientific case grows stronger with each new finding. What Pluto teaches in the end is that distance is not the same as irrelevance. The fact that a world is far away does not mean it is simple, dead, or uninteresting. It often means only that we have not yet looked closely enough. The same lesson applies with greater force to the thousands of other icy bodies in the outer solar system and to the countless cold worlds orbiting other stars. Each of them is a place. Each has its own physics, its own chemistry, its own history. Each, when observed with sufficient care, will likely turn out to be stranger than expected. Pluto was the warning. A familiar name, a familiar story, and beneath both, a reality that took nearly a century of careful work to begin to perceive. The cold, distant, quietly active world that Webb has now described is the real Pluto. The version we grew up imagining was always a placeholder, a stand-in we accepted because we had nothing better. We have something better now, and the something better is not comforting. It is fascinating. That perhaps is the more accurate way to end this story. Not with horror, but with the recognition that the universe consistently rewards careful observation by replacing easy comfort with something more interesting. The real Pluto is not the lovable underdog. It is a frontier world running on chemistry that we are only just learning to read. It is a laboratory for understanding atmospheres, climates, and surfaces across the outer solar system and beyond. It is a reminder that the cosmos is full of places that do not match our expectations, and that the gap between expectation and reality is where the most interesting science always lives. The James Webb Space Telescope will keep observing. The data will keep arriving. The story of Pluto will keep growing more detailed, more nuanced, and almost certainly more surprising. And somewhere on the dim outer edge of the sun's influence, a small frozen world will keep doing what it has always done. Turning slowly, breathing out faint traces of nitrogen, glowing dimly in infrared light that no one will ever see with their own eyes, quietly being itself, regardless of what we choose to call it. That in the end is the most honest description of Pluto that can be offered. Not a planet, not a dwarf planet, not an underdog, just a world. Real, distant, strange, and finally, after nearly a century of guessing, beginning to be seen.